In this video, we are going to look at some applied optimization problems. In this first question, we are given that a rectangular pen is being built with one side against a barn. So this is the pen. 200. So what is given to us is that 200 meters of fencing are used for the other three sides. What dimensions maximize the area? So what I'm first going to do is declare some variables here. So let's make this x, this also x, and this to be y. So what is given is that 2x plus y is 200. Okay, so now this is our constraint equation. So we have only 200 meters of fencing material that we can use. Okay, now what is our objective? Our objective is to maximize the area. So this is a rectangle. The area of a rectangle is given by length times width, right? Now, we do not want an equation in two variable. So we are going to see how we can use the constraint equation to rewrite it so that one variable is written in terms of the other. So what I'm going to do is I'm going to take this constraint and I'm going to rewrite this as y is equal to 200 minus 2x. Okay. Now I'm going to take this to the area equation and I'm going to replace my y with 200 minus 2x. Now, if I distribute this, I can rewrite my equation in just one variable. So what I have done here is I have written my objective function, the area, as a function of x. Now I need to find what is the domain of this function. And to do that, if I look at this constraint that I have, I know that x has to be, so in order for y not to become negative, right, x has to be less than 100, right? So basically, my domain will be anything between 0 and 100, right? So this is my domain. So knowing all of this, my goal is to find the dimensions that is going to maximize this area. Now, before we even proceed, we know that this is going to be, if you were to graph this area function, it's going to look like something like this, right? So basically what we are trying to find is what is this x value, right, for which the area that you get is the maximum. So what we're going to do is we are going to take the first derivative, right? And this is what we get as the first derivative. We find the critical point by setting this equal to 0 and solving. X becomes 50. Now we have to see if this is a maximum or a minimum or whatever. So in order to do that, what we are going to do is we are going to use the second derivative test to find local maxima and minima, and then we are going to make this conclusion about an absolute maximum and minimum from there. So what I'm going to do is I'm going to find the second derivative. The second derivative is just -4, which means the second derivative evaluated at the critical point, the second derivative does not have x in it, so it's always going to be negative. -4 is always negative, so this is always less than 0. So if this is less than 0, what it means is that we have a concave down shape of the graph and you have a critical point here. So this critical point has to be your local maximum. So my conclusion is that x equals 50 is my local max. Now, how do I know that this is also the absolute maximum? If you look at your endpoints, right, when x is 0, what happens to the area? When x is 0, my area is going to be 0. When x is 50, not sorry, 50, 100, my area is still going to be 0, correct? So basically, my two endpoints are going to be like this, 0, 0 and 100, 0, right? Which means that this value has to be also the absolute maximum. So now I have found the x value that gives me the maximum area. I calculate the corresponding y value by going into this equation. Y is 200 minus 2x. So if I plug that in, I have 200 minus 2 times 50, which is 100. So the answer to this question is the dimensions that maximize the area are 50 meters by 100 meters. Okay. Okay, the next problem. This rancher now plans to make 4 identical rectangular pens against a barn, each with 100 meters squared of area. What dimensions will minimize the amount of fence used? Okay. So now here, what is the constraint that they have given to us? The constraint here is that okay, so first let me do this. Let me make this all x, 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 x. Okay. Um, or rather, let me do, oh, it doesn't matter. And so this becomes y, right? And I'll make all of these to be y's also, okay? If I do that, what is my constraint here? X times y is 100, correct? That is my constraint. Now, what is the question is asking you what dimensions minimize the total amount of fence used? So, what is the total amount of fence used? I have 1, 2, 3, 4, 5x plus 4y, right? That is my amount of material used. Now, I'm going to just call this P, right? So, this is what it is. My goal is to minimize that. Now, again, we know that we don't want two variables, so I'm going to use this to rewrite one in terms of the other, okay? So then I'm going to plug this in so that I can write my function in just one variable. So this is what I have. So I have a perimeter function, which is written as a function of x. Now the domain here is that x has to be greater than 0, okay? So this is my objective function. Okay, so I have my objective function. I know the procedure now to find the critical point. I take my first derivative. I have 500 minus 400 over x squared, which can be written as 5x squared minus 400 all over x squared. So to find the critical points, I set my numerator equal to 0. I take the 5 away. I have x squared minus 80, right? Am I right? Okay. All right. So which means x is equal to plus or minus square root of 80. Okay, so the denominator gives me x equals 0 as a critical point. But what I know is that this is not in the domain. Negative root 80 is also not in the domain. So there is only one value that I'm interested in, which is x equals square root of 80. Now I need to make sure whether this is a maximum or a minimum. So what I'm going to do is I'm going to take the second derivative. If I take the second derivative, what do I have? The 5 goes away. I have this, right? So this will become 800 over x cubed, right? And if I evaluate it at this critical value, it is going to be always greater than 0, right? Because this is positive, positive raised to cubed is also positive, so it is greater than 0. So what this tells me is that I have a concave up graph and my critical value is here square root of 80, right? So that means this is going to be my local minimum, right? Now, how do you make sure this is also the absolute minimum? Now look at the two endpoints, right? So one of the endpoint is, so we have x has to be greater than 0. So 0 to infinity is my domain. So now x is On one end, when x is close to 0, what happens is that this becomes almost close to 0, whereas this goes to infinity. So you have on one end, your function is going to infinity like this. Now, when x goes to infinity, what happens? This goes to 0 and this goes to infinity. So the other end also is going to infinity, correct? So which means that this value is going to be my absolute minimum. So then I'm going to say that the dimensions that minimize material used will be square root of 80, what is that, meters, and y will be 100 over square root of 80. Okay, that's what we have. Okay. A box-shaped shipping crate is designed to have a volume of 16 cubic feet. The material for the base costs twice as much as the sides. Material for the top costs half as much as the sides. Okay. One second. So this question does specify that the base of the box is square shaped, okay? So you have a square shaped base, right? So this is our box. So we have x as our base and our height, let's declare it as y. Now, what is our constraint here? Our constraint is that the volume, which is given by area of the base times the height, has to be 16. Okay. What is our objective? Our objective is to minimize the cost. So if the question is specifying the material used, they're talking about the surface area, okay? So what is the surface area? Now you have one base and one top. The area of the base is x squared. The area of the top is also x squared. So x squared plus x squared is 2x squared. And then you have four sides which have an area of xy. So you add them all up, that is 4xy. So this is the surface area of the box, okay? Now, but we are interested in the cost, right? So what they have told is that the material of the base costs twice as the sides. So let me say that C be the cost of material per square feet of the side, okay? So now if I'm writing a cost function, what happens? So the side cost will be 4xy times c, right? Whereas the base cost will be times 2 times c, because they told you, no, wait, material for the top costs half as, wait, oh, okay, let me just split it up then, I'm sorry. So this needs to be split up. So the top costs, so according to them, the material for the base costs twice as much as the sides. So base is this times 2c. And then they are saying that the material for the top is half as much as the sides. So the top is also x squared, but it is 1/2 of the side. Okay, so this is what we have. Okay, so now if I combine all of this, what do I have? I have 2cx squared plus 1/2 cx squared plus 4cxy. Now the first two terms can be combined to write 5/2 cx squared plus 4cxy. Now I'm going to use my constraint to rewrite my y in terms of x. And then I'm going to bring it here so that I can write my cost function just in terms of one variable x. Okay, so this will be replaced by 16 over x squared. Now I combine all of this and I will get this 3264 c over x. This is my cost function in terms of one variable x. Okay, is it a correct? Okay. Now here again, my domain is x has to be greater than 0. Okay, so I do the same thing that I did before. I'm going to take the derivative, first derivative. So I will have 2 times, so this will become 5cx minus 64c over x squared. Is that right? Okay. So now I set this equal to 0, right? Now I'm going to rewrite this like so. I'll set the numerator equal to 0 and denominator equal to 0 separately. Okay. So c cannot be equal to 0. C is a constant. Let's forget that. So which means x cubed is 64 over 5, or x is cube root of 64 over 5. The denominator gives me x is equal to 0, but this cannot be a critical point because it's not in the domain. All right, so I have only one critical value, which is this. Now I need to take the second derivative to see if this translates into a local maximum or minimum. So I take the second derivative, I will have 5c plus 128. I have this. So now if I evaluate this as this critical value, this is definitely going to be greater than 0, right? Because x is positive and everything is positive, so greater than 0. So that means I have a concave up function, and this is my critical value. And using the same logic that we had before, you know that this side is going to infinity, this side is going to infinity, therefore this has to be the absolute minimum also. So then what we are going to say is that the dimensions that minimize the cost will be x is cube root of 64 over 5. The unit is feet, and 16 over x squared. Okay. Y will be 16 over 64 over 5 to the power of 3 halves feet. I mean, you can simplify this or just leave it like that. Okay. I'm sorry, it's not 3 halves. It was 2/3. Because it was x squared, right? So cube root x squared. Okay. And this is what we have as the dimensions. Okay, next one. Find the radius and height of a cylindrical soda can with a volume of, so we have a cylindrical soda can now. Radius and height of a cylindrical soda can. So let this be R, this be H. So we want to find these dimensions with a volume of 354 cubic centimeters that minimize the surface area. Okay, so what is my constraint here? My constraint is that volume is 354. Volume of a cylinder is pi r squared h is 354. What is my objective is to minimize the surface area. The surface area is the base is pi r squared, the top is pi r squared. Add them up, you have 2 pi r squared plus 2 pi r h is the surface area. Now I'm going to rewrite this like so. H is 354 over pi r square. And then I'm going to take that here and I'm going to replace my H with 354 over pi r squared. So this gives me my area function in one variable r. So if I simplify this, the pi and the pi goes away, one of the r's goes away. This will become 708 over r. This is my area function. So then what do? I go ahead and take my first derivative. I get this. Set it equal to 0. Again, my domain is r greater than 0. Set your numerator equal to 0. Factor out the 4. So that is 1, 20, 70, 28, 177. Is that correct? 77 times 4, 28, 223. Wait, 28, 2. 28 plus 2 is 33, 708. Okay, so we have that. Then we set up pi r squared minus 177 is equal to 0. Simplify this to solve for r. R will be cubic root of 177 over pi. Okay, now this is my critical point, right? So then I'm going to take the second derivative. So my second derivative is going to be 4 pi plus 2 times 708 will be what, 1416 over r cubed. Now a double prime at cubic root of this is going to be greater than 0. So we have a concave up with this r as our critical value. So therefore, this is going to be my local minimum and two ends going up. Therefore, it is also the absolute minimum. So what are the dimensions of the can that I'm looking for? Or radius is cube root of 177 over pi. Unit is centimeters. And h will be 354 over pi r squared centimeters. Okay, so that is our answer. Okay, in this last question, we are given that a window consists of a rectangular pane of glass surrounded by a semicircular pane of glass. If the perimeter is 20 feet, find the dimensions that maximize the area. Now, let's make these dimensions x and y of the rectangular portion. So what is my constraint here? My constraint here is that the perimeter is 20, correct? So that means the rectangle perimeter is x plus 2y, because this is also y. So the perimeter is going to be x plus 2y for the rectangular portion. And then here for the semicircle, the circumference is 2 pi r. And in this case, r will be x over 2, correct? So that will be 2 but that is for a circle. So for a circle, the circumference is 2 pi r. So in this case, your r is x over 2, but this is a semicircle, right? So because this is a semicircle, I'm going to have this as pi x over 2. So now this whole thing becomes my perimeter, right? And according to what is given to me, it's given that this whole thing is equal to 20. Now, what is my objective? My objective is to maximize the area. So the area of the rectangle is xy. The area of a circle is pi r squared, but this is a semicircle. So half of pi r squared, r in the case is x over 2, the whole squared. Now I want to minimize this area. So to do so, I'm going to obviously rewrite this in one variable, right? So that means I have 2y is 20 minus x minus pi x over 2, which means y is 10 minus x over 2 minus pi x over 4. Okay. So now I'm going to take that here and I'm going to substitute 10 minus x over 2 minus pi x over 4 plus pi x squared over 8. That is my area function in terms of x. Okay. If I want, I can distribute it 10x minus x squared over 2 minus pi x squared over 4 plus pi x squared over 8. I can combine the like terms here to give me minus pi x squared over 8. Am I right? Okay, I think I am. All right. So this is my area function in terms of one variable. All right. I'm going to go and take the first derivative of this. So I have negative 2x over 2, which is just x, minus negative 2 pi x over 8, which is negative pi x over 4. Now I'm going to set this equal to 0. So basically what I have is x plus pi x over 4 is 10. So 4x plus pi x is 40, right? So x times 4 plus pi is 40, which means x is 40 over 4 plus pi. This is my critical value. Is that correct? Okay, so then I go and take the second derivative. The second derivative is going to be negative 1 minus pi over 4, right? So the second derivative evaluated at this critical value is less than 0, which means I have a concave down with this critical point, and this makes it my local maximum. Okay, so since we know that this is also an absolute maximum, we are going to say that the dimensions that maximize the area are, this one is my x value, and my y value is 10 minus x over 2 minus pi x over 4. So I just substituted, and this is what you get as the y value. And the unit is feet.